I'm delighted to welcome our speaker today. Our speaker is Zach Amato from the ISIS Neutron and Muon source at Harwell in Oxfordshire here in the UK. Um, and we're going to have a presentation followed by a Q&A. Thank you, Martin, for the links already in the chat. I've got some introductory stuff for you, Zach, but can I hand over to you to introduce yourself? I feel like that's a nicer transition.
Yeah, of course. Hi, everyone. Yes, my name's Zach, and my PhD was actually in astrochemistry, and it was half funded by the OU, the Open University, the ISIS neutron source, where I was using neutron scattering to look at porous ice in star-forming regions, and I was using neutrons to study the structure of them. And then once I finished my PhD, I spent a year being an instrument scientist at ISIS, so I was running one of the instruments there. And I was starting my own research more in the planetary science side of things, where I was looking at the structure, where I look at the structure of liquids and ices across different planets and so on. And now my current role is I'm still half ISIS and half Queen's University Belfast, where I run an X-ray facility here and I continue my research. That's probably a good, decent enough synopsis there.
Fantastic. Thank you, Zach. Okay, the floor is yours whenever you are ready.
Lovely. Let's see now if this decides to play ball again. And then, all right. Is that working?
Looking good.
Yes. Perfect.
All right, perfect. I guess I will kick off then. Yeah, thank you guys for the intro. So yeah, today, so I assume lots of people maybe will have heard of the X-ray world, X-ray diffraction and so on. But I think neutrons, especially in planetary science, are maybe not so known, even though neutron scattering is very widely used across many different scientific fields. So I thought today I'd give you essentially a sort of whistle-stop tour of some of the main techniques, especially for looking at structure. Neutron scattering is very much a toolbox of techniques. It's not a one thing. There's many different things you can do with it. There's many different types of instruments. So I'm going to try my best to keep things nice and basic and surface level, just to give you a flavor. And obviously, then if you have more questions, just chat to me. I'll also be running an ISIS booth at EPSC, so you can come speak to me also in person there as well. So obviously, there's been, over many decades, there's been lots of different ways to look at structure, and many people have used these things because these are nice benchtop based things. So whether that's microscopy, going over to electron microscopy, these are really great, of course, because they're easily accessible and so on, but they do have a limitation on how small you can get to. And even if they do get to very small, a lot of the time you're only really getting qualitative information, which is, of course, limiting for different applications. And even spectroscopy, which, of course, we use a lot in planetary science and astrochem, the problem there is that this is a very indirect way of actually measuring structure. So X-ray diffraction usually bypasses a lot of these issues. So it is a direct way of measuring bulk structure, and you can get down all the way to atom distances. And this is a fairly known technique because quite a few universities and institutions will have a lab-based XRD, like shown here. Let me see if I can get a little laser pointer while I'm at it. Yeah, so showing like the XRD here. And even actually the Curiosity rover has an XRD on board. And we can see that from the XRD pattern here on the left, where they looked at Martian soil, and that diffraction pattern let them see that there was crystalline feldspar, pyroxenes, olivine, all mixed in with lots of amorphous non-crystalline material. And we know this because these things will have unique patterns, which I'll talk more about later on. Now, X-ray scattering does work from a theory perspective very similarly to neutron scattering, but there are some key differences, which is why some people might use neutrons for specific things or X-rays, or use both as complementary techniques. The main difference is what the things are scattering off of. So the X-rays are interacting with the electron clouds of the atoms that they're scattering off of, whereas the neutrons are interacting with the nucleus of the atom. And so X-rays are therefore far more sensitive to heavier atoms, as can be seen here, because they'll have more electrons to scatter off of. Whereas neutrons then have no trend. When you look across the periodic table, there's no trend in how well they scatter off of things. And so this makes it possible then to maybe differentiate any elements that are maybe next to each other in the periodic table, or you can pick out light elements, even though there are also heavier ones in the same sample, which is usually quite difficult to do with X-rays because the heavy elements kind of drown out the light ones. And so neutrons also have a very unique ability to then differentiate between isotopes, which I will talk a bit more about later on as well. So the overall benefits of using neutrons, why do we bother? Well, because the neutrons are neutral, that means that they interact very weakly with condensed matter, and that means they can penetrate a sample very deeply, really helping with it being a bulk way of looking at structure. It also means that it's non-destructive. So it means that it's great if you have any sensitive samples, especially if you're doing soft matter studies or looking at proteins. The great thing is that the beam is not going to damage them. And then lastly, especially when it comes to our kind of work, you can look at your samples in complex sample environments. So you can put them in pressure cells, you can use them in vacuum chambers and so on. You can do all sorts of in situ measurements, which is harder to do with X-rays. So this all works because of the fact that at room temperature, we can see that neutrons have an energy of about 25 millielectron volts. And that essentially corresponds to a velocity then of 2,200 meters per second. And the main thing is that it ends up being that the neutron has a wavelength of 0.18 nanometers. And this wavelength, in terms of structure, is equivalent then to the sort of atom-atom distances and things that we want to look at in our samples. And so this happy coincidence means that we can use neutrons to study structure at room temperatures, normal operating temperatures, which is really, really fantastic. And we're very lucky on that one. So what happens in a neutron scattering experiment? I mean, same in an X-ray one. Essentially here, you have an incoming neutron, and that neutron will have a certain wavelength, it'll have a certain energy before it hits your sample. And then when it hits your sample, it's going to scatter off in many different ways through certain angles and so on. And what we do is, of course, we detect all these neutrons that are firing from your sample across lots of different angles to see where it's all coming through. And we measure our intensity of these neutrons that are scattered as a function of something called Q, which is just a momentum transfer. The only thing you need to understand of what that is just that it's inversely proportional to wavelength, which means that it's inversely proportional to the length scale that you're looking at. So if you measure small values of Q, you're looking at large distances, you're looking at larger things. So actually, if you want to look at atom to atom distances, really small distances, you want neutrons to have a very short wavelength so that it's comparable to the length scale that you want to access. So the instruments are very much designed, keeping this in mind, with putting detectors in a certain way and using a certain type of neutron beam. All of that is taken account to based on what you want to look at. So how well something scatters in terms of the atoms or things that are the elements that are in your sample has to do with something called their cross-section. And as the name kind of implies, a cross-section is kind of like an area. You can kind of think of it like the effective area of the target that the sort of neutrons have to hit in order to have a particular scattering process happen. And the larger the cross-section, the higher your scattering probability. So the larger the cross-section, the more likely the element in your sample will scatter. And what's really important, which again, I'm not going to delve too deep into, but there's two main parts of this total cross-section. We have something called a coherent and an incoherent cross-section. And where the bit of the coherent cross-section is to do with the arrangement of your atoms. So that just means that that's the information to do a structure in your sample. And if you're looking at structure, the incoherent part kind of just provides a flat background. If you're looking at dynamics, which we have instruments for, I'm not going to go too much into detail of those, but there you'd want to be honing in on the incoherent. But the important thing to look at here is that there's a very big difference in the hydrogen and deuterium cross sections. You can see that the hydrogen has a huge incoherent cross section, which means that it has a huge background, which is difficult to get rid of when you're trying to look at structure. Deuterium doesn't have that problem, which is why it's very common for us to swap these two, and that's used heavily across all of the different fields of neutron scattering. So you can essentially exploit these differences between isotopes, specifically that hydrogen and deuterium difference, and you can use that to get much more structural information than you would normally get at just looking at the sample as a bulk. And this is very unique to neutrons. We cannot do this with X-ray scattering. And so what you can do, if you selectively swap hydrogen with deuterium in certain parts of your sample, you can highlight them. So you can have lots of different samples where you selectively deuterate different things. So for example, if you have a protein in solution and you want to focus on the head of the protein, you would selectively deuterate that bit, keep the tail hydrogenated, and then have that essentially visible. And you can then play around with that. And so there's a lot of power in doing this. There's a lot more information you can get then. So with neutron scattering, when you're looking at structure, there's a wide range of length scales that you can probe depending on the instrument that you use. And yeah, unfortunately, you can't have a universal neutron scattering instrument that does it all. And you do need to have many different types of instruments because those length scales that you access very much depend on the detector positions, the neutron energies, and so on. So these will be tailored to the science that you're looking at. So the first technique I'm going to talk about is the one that's probably more known to people, especially if you've done X-ray work, which is just sort of traditional diffraction. And so that's where you're characterizing the structure of crystalline materials. So that's anything that has a regular periodic arrangement of atoms. So that could be certain phases of ice, that could be metals and so on. And so for a crystalline solid, the neutrons as a wave, if anyone's done a bit of physics or physical chemistry in the past, essentially they go through, they get scattered by this lattice, and you can then figure out the sort of distances between these planes and so on because of the fact that you know the wavelength of your neutron, and then you can use what's known as Bragg's law to then decipher your whole crystal structure. There's sort of two types of diffraction instruments. There's single crystal and powder diffraction. So the single crystal version is very much in the name. You put a single crystal of your sample, you throw some neutrons at it, and you see how all of that scatters. And so one example is shown here, where all of these dots are sort of the maxima of where there's high intensity neutrons being scattered. And that has to do with your crystal structure. The problem, though, is that for most samples, it's really hard to make a single crystal that's big enough to get good resolution. So predominantly, we do then the powder diffraction method instead, where essentially you powder your material, put it in a container, and then scatter from that. And instead of having those dots, you're going to have a much more smeared version. But when you reduce that data from the sort of image down to your 1D, you'll get those sharp Bragg peaks. And these peaks that you see, that's where you get your information of your crystal structure and also what's in your sample. So the peak position, where they are, will have to do with your crystal structure, the phase of your material, what's in the material, because things will have a specific fingerprint in a sense. The intensity will give you some information on atomic parameters, if there's any preferred orientation, and the shape of them will tell you how crystalline your material is, if there's any disorder. So if there's disorder or something is more amorphous, there'll be a fattening of the peaks rather than having sharp ones like shown. So one example of a planetary science study done at ICIS is looking at the structure of ice mixtures of ethanol and ammonia, which are of course relevant to cometary ices and also other astrophysical regions. And they looked at the diffraction patterns then of two different types of these mixtures, one which was an ethanol monoammoniate and one that's a hemiammoniate. And they were looking at this at temperatures between 175 and 195 Kelvin in situ. So these are the patterns shown. And from fitting to these patterns, these diffraction patterns, they could then resolve the entire crystal structures. And they found that the ethanol monoammoniate is characterized by having sort of linear tapes of four-sided hydrogen bonded rings, and these extend along one axis, whereas the hemiammoniate is then, the structure of that is defined by having more sheets and have different types of hydrogen bonded rings. Instead, it'll have four and six-sided hydrogen bond rings. And taking that structural information out, they could also get precise determinations of any thermal expansions and so on. They could see that both of these phases, these mixtures, will undergo some proton transfer reactions where they create then a pure salt, or they might also create an ionic co-crystal. And so that could be a really important mechanism for some of the spectroscopic signatures that we're getting in data from cometary and planetary ices and so on. Then if we go on to, this is going to work. Yeah, there you go. So that was looking very much, yeah, atom to atom distances. It doesn't have to be for purely crystalline materials. You can have ones with defects in, and so on. But now we'll go on to sort of the larger stuff. So if we zoom out more from the atom to atom, so this is called small angle scattering. And so, yeah, so this is where we're looking at larger things. So it might be proteins, micelles, microemulsions, porous materials, and so on. We tend to refer to this just as SANS, small angle neutron scattering. And so this is not just looking at crystalline materials. And so the clue in how this works is that we're looking at the neutrons that are scattered at very small angles because these are equivalent then to small q values. Sorry, yeah, small q values, which means that we're looking at large things, big things. So we get our 2D pattern from that again, like we saw with the diffraction. We reduce it, we get a curve. And instead of having these peaks that you saw before, you're going to get a curve where the shape of this curve has to do with the shape of the things that the neutrons are scattering off of. So for example, if you have nanoparticles or a protein in solution, if those particles or protein are in a sort of cylindrical shape, that will look very different to if they were more spherical and so on. And these are things that you can all gauge from the shape of these curves. And you can also get information on their size and so on. You can also then look at surface area of these materials. So I've used this to look at porous ice, where I could get size and shape of my pores. I could get how porous they are and what their surface areas are and so on. And that's all to do with different sections of the curves, meaning different things. And you fit models to them to get this information out. So just to give some examples, there's been people looking at size and structures of colloidal aggregates in proteins and so on, affected by different pHs of their extraction processes. There's been people looking at porosity of catalysts to optimize them. And there's also been people then shown on the right looking at a new material for liquid hydrogen storage used for rockets, of course. And they looked at this graphene integrated into an aluminium alloy, and they could use SANS to look at the distribution of the nanoparticles in this composite. And they could see that they were evenly dispersed across the sample. And they could also look at how this distribution then impacts things like precipitation kinetics in their material. So there's lots of stuff that can be done with this technique. So obviously with that, I'm keeping things fairly brief, but of course you can chat to me more about all of these, but lots of options to be done there as well. Then the group that I'm in at ISIS is called the Disordered Materials Group. And we are looking more, we have several instruments where rather than just looking either at crystalline materials or looking at, say, things in solution or we specialize in looking at bulk structure of materials that are disordered. So that could be liquids. So getting bulk structural information on things like liquids and glasses where they don't have long range order like a crystalline material might have. They'll have a bit of local ordering, but then when you zoom out, it becomes much more disordered. And so how do we characterize the structure of something like a liquid and so on? And so we can't use these conventional crystallography techniques. We use a method called pair distribution function, or PDF for short. And this allows you then to essentially determine lots of different interatomic distances occurring in a sample. So the best way to kind of imagine it is imagine that you're sitting on a water molecule and you're looking out to your neighborhood and you're mapping out where are the other water molecules and how close are they to me? How many of them are there in these different shells? And that's essentially what's kind of shown here. And then you keep zooming out, and all of these peaks are equivalent to this, to looking at your neighborhood. And it's actually then much more powerful. Oh, is this gonna? Yeah. It's much more powerful to actually turn this into something called partial PDFs, where instead of just doing water to water neighborhood, you might want to do instead oxygen to oxygen, or oxygen to hydrogen, or hydrogen to hydrogen. People that have done simulations will have likely done this. There it's referred to more as G of R's. And so that's the same thing of mapping out, I'm sat on oxygen, where are the next oxygens? And this gives you a lot more information because you can look at things like hydrogen bonding or orientations of things like that. So how do you get this information out of a neutron experiment? Well, you get your experimental curve like we saw before, and you'll see the difference if you have a crystalline material. Again, we have those sharp peaks, but when you have something like a glass or a liquid, these would be much broader features. And what you can do is you can take that data you get from the neutron experiment, and then you can do something called a Fourier transform, which you don't, luckily software does all this for you. And then that essentially turns it into that PDF that I've just spoken about. But then again, taking it from that structure, you're getting the overall PDF. But if you want to get those partial PDFs of the sort of, yeah, example for water, oxygen to oxygen, oxygen to hydrogen, what we do to get that is play the game of that isotopic substitution, that swapping of hydrogen and deuterium, like we spoke about before. So you can see on the right-hand side, the H2O scattering looks very different to D2O, and then it looks even more different to, yeah, 50-50 mix of these two. And so by having these three different samples of the same overall sample of water, we can use that to extract all of this more detailed information. And then what we really specialize in is taking that neutron data, those different samples, all of that data, and we use it to then refine a simulation. Because of course with computational simulations, you can get even more information on things like dynamics or getting atomistic understanding. So what we do is we build up a simulation box with the potential, how you do normally when you set up a simulation. From that simulation, we calculate what would the scattering look like if we were to throw neutrons through it. We then compare that to our neutron data, and if they don't match, we refine the simulation. Essentially, we keep repeating that until they do match. And once we've done that, we can then go on to do other analysis that you can only really do with simulations and you can't get out of your experiment. For some examples, so some of our long-term users have been studying the role of magnesium perchlorates in the subsurface water on Mars, and this is using several instruments at ISIS. And so they did that thing of selectively swapping hydrogen and deuterium, and they used this to find out that having magnesium perchlorate in liquid water makes the liquid water structure look like it's under massive, massive pressure, even though they're not applying any external pressure. And so you can see this here, where this essentially shows how our water molecule is oriented around another water molecule. And you can see that in the presence of the perchlorate, it's much more compacted in. So they then went on to see, well, what happens if we add an amino acid like glycine? Could that still self-assemble under these conditions? And they found that, yes, although the magnesium perchlorate is disrupting that hydration and hydrogen bonding ability of the amino acid is still able to self-associate. And they seem to happen more readily at low temperatures. And so it seems that it is possible to have biological molecules forming in that Martian environment. And then their last more recent finding was that if you add in then an osmolyte, like in this case, TMAO, it seems that can undo the pressuring effect of this magnesium perchlorate on water. And that could then help prevent any damage to biological systems in these conditions. Another example, which is far more recently this year, is my own work with my collaborators at the Northern Arizona University and also University of Reading here in the UK. And this is actually the first ISIS and Europlanet transnational access scheme experiment, where we wanted to study the bulk structure of liquid methane, ethane, and propane, as of course relevant to the lakes and seas of Titan. And what we did is we were flowing in the gases to condense in situ in a pressure cell on the beamline at 95 Kelvin. And we also did one set of samples where we'd flow in nitrogen to simulate nitrogen dissolution from the Titan atmosphere into the lakes and to see how this all impacts structure. We have more beam time scheduled next year now to look at mixtures of these alkanes so we can understand the exotic behavior we've seen in spectroscopy work beforehand. All of this analysis is still ongoing, but here are just some scattering curves to show. And looking on the right side, this is again imaging of looking how methanols are arranged around each other. But that will eventually come out at some point. But I thought I'd show that since that's especially the first Europlanet one we've done so far. And then my own PhD is a bit different to what people would normally do in our user community, which is we have one of our instruments is a hybrid SANS and diffraction. So that just means it can simultaneously look at a very wide length scale range. at one time. So what we did is we created this high vacuum chamber that has a plate in it with a capillary that sprays any vapor onto the plate that can be down to 20 Kelvin, very cold. And so we made lots of different samples of water ice or amorphous solid water and wanted to look at the structure of this as a function of deposition temperature and annealing. And so here's an example of what that data looks like. So we can go from about zero point 0.1 angstrom all the way to 300 in one measurement. And so what's great here is we can simultaneously see that is the ice amorphous or not, and also how porous is it, and how much surface area is it, and so on. And so we can see when we anneal this sample that was deposited at 40 Kelvin, that past 140 Kelvin, the ice becomes crystalline because these Bragg peaks appear, and there's this flattening of the curve that you can see on the left, which has to do with then a loss in porosity and surface area, which we can get quantitative values for, and so on. We saw then with all of this work that amorphous solid water, at least when it's made through vapor deposition, seems to be of two main populations of pores rather than a uniform distribution. It looks like the ice is actually made up of these nanoporous grains that are separated by larger voids. And even after crystallization, there's still porosity left over from those voids persisting, and that has a big impact on chemistry. So there's a very new image of what this interstellar ice looks like, which is, yeah, what the foundation of my PhD were about. So moving on from that, one other study is reflectometry. So everything we've looked at is very much sort of bulk structure. The neutrons just go through your entire sample, and you're looking at an average picture of your bulk structure. But with reflectometry, this is a sort of surface technique. So this is if you want to look at sort of the composition and structure of different layers or films on something. And so you can use this, you can study thicknesses of different layers up from like 10 to 5,000 angstrom. And depending on how you send in your beam, and so this is where you bring it in at a grazing angle, depending on how you bring that in, you can access buried interfaces or buried layers. And again, you can use that selective swapping of hydrogen and deuterium where you could make some layers invisible if you want to focus on different ones and use this technique for that. So one example, which is not planetary science related, but could be in a sense because it's atmospheric work. So this is where they were looking at real and proxy atmospheric material because they wanted to estimate the surface morphology and the thickness of aerosols and how this changes over their lifetime. And because neutrons can penetrate through the materials and look at really the structure of really extremely thin films of only a few nanometers thick, they could observe then in real time how ozone alters the organic films on these aerosols. And they used these results then to put into an atmospheric model to estimate how much an aerosol would heat or cool the atmosphere over its lifetime. And then we can also do imaging. So you've probably maybe seen some X-ray imaging, of course, but we can do that with neutrons. And so we can use special neutron imaging detectors to do exactly that of where, of course, here the differences you'll see on the right side. The bottom one is an X-ray image and the top one is a neutron image. So this again has very much to do with the difference in how things are scattering because X-rays do scatter off better off of higher electron density things, so heavier atoms. Essentially, it's very hard for the X-rays to fully penetrate through the heavier bits of the camera, whereas that's not the case for neutrons. So it's very normal to maybe use both X-rays and neutrons as complementary techniques here to get more information on your sample or whatever you're looking at. You can also do tomography, where you're rotating your sample and then you can construct a 3D image. And here they wanted to look at water uptake in plant roots because you can image very quickly over seconds. You can take quick snapshots. And they use that hydrogen and deuterium swapping to look at water uptake dynamics and figure out the mechanisms happening there. So here's just, yeah, a summary slide. It probably feels, yeah, I'm whizzing through them and I've only really touched the surface of them. But yeah, so this is just give out, there are many different techniques and it's all, yeah, you go to these different groups or different instruments depending on what it is you want to find out about your sample. So some people will just take their one sample or multiple samples to lots of different instruments to get a whole host of information. I didn't delve into it, but yeah, we do have a whole host of instruments that are looking more at dynamics of things, where instead of focusing on the direction of where the neutrons are scattering, you're focusing on the change in energy of the neutrons. And so you can look at that, you can use that to get quantitative information on dynamics of, say, reactions or things in your sample. You can do spectroscopy with it. You can look at magnetic properties and quantum excitations and all sorts of stuff. But don't ask me too much on this because that's definitely not my expertise. But all right, so I've explained kind of all the different things you can do, but where do you go to do this then, right? So here is a map of sort of the major neutron beamlines across the world, and some are private and some are public. And the main two public sources for Europe are ICES in the UK and the ILL in France. There is also the ESS being built in Sweden currently, but there's still a few years before that's fully open. So with public neutron sources, you submit a proposal that will then be judged by a panel, and you'll get awarded a certain amount of beam time if they accept it. Like if you're applying for telescopes, it's the same idea. And although that might all seem quite daunting, you will get a lot of support with the experiment and also the analysis and also the proposal writing and design of your experiment from people like me, the instrument scientists that run the instruments. Don't let any of that put you off, that it might seem like difficult to learn. That's what we're here for. So ICES is located in the Rutherford Appleton Lab in the UK, and it's run and funded by one of the branches of our government. It also encompasses Ralph Space, which you've likely heard of since they built, I think it was MIRI, for the James Webb telescope. We also are next to the Diamond Light Source, which is for an X-ray synchrotron, and there is also the Central Laser Facility in the same lab. And so ICES itself, we are a world-leading center for research, and we have two main target stations, and we have 29 neutron instruments across them. And at the heart of ICES then is an 800 mega electron volt proton accelerator, which is creating pulses of protons 50 times a second that get fired off to these target stations. I'm intrigued if this is going to work. Oh, yeah. So at the very start, there's an ion source, and that's creating some negative hydrogen ions. Those electrons get stripped off before they go into our big circular synchrotron. They get basically whizzed around until they travel at about 84% of the speed of light. And then those protons will go off to our two target stations. They'll collide with a very heavy tungsten target, and that creates neutrons through the spallation process. And those neutrons go off to our different instruments. I think, as you can see, hopefully that is working, but I'll pray for it. It's a bit, it doesn't always work, that video. But to give you an idea, this is what the inside of these target stations look like. In the middle over here, hard to see in this image, but the target is there, and then all the instruments are under the floor, but they're all being shot off from that central target. You can see it a bit better here in target station 2, which is a newer target station. The target is in here in the blue bit, and then you can see the sort of guides coming off. And every year we get about, I don't know how recent these numbers are, but we get about 1,600 proposals from about 35 countries. Lots of experiments, lots of people coming, luckily lots of papers too. But I thought it'd also be worth mentioning, of course, as I said, Diamond Light Source is our neighbor, and you can actually access Diamond through the same proposal that you put into ICES, because these are very complementary techniques because of the differences in what these are sensitive to. So it's very normal to go between the two. So what you can do is when you put a proposal in for ICES, you can tick a box that says that you also want complementary X-ray information. And so you don't have to do two proposals. And so one of the benefits of X-rays is that they're much faster in their measurements. So you can get down to like microseconds, whereas with neutrons, it's more minutes or hours. So if you're doing lots of in situ stuff, sometimes it's good to also do the X-rays because they can do much quicker snapshots of your structure. And so lastly, I just wanted to explain that we are, of course, now part of the Europlanet Transnational Access Scheme. This is for the crystallography group and the disorder materials group. Because although, yes, the beam time is free at ICES for anyone, any academic, it's free to use, but we only cover the accommodation and travel cost for UK-based people, unfortunately. So for those that are not UK-based, if you want your travel and accommodation covered, you can apply through the Europlanet scheme to get that money covered for you, luckily. And that one is you'd apply through us, get your beam time, and then you can apply to Europlanet to get that money in. And that's what we used for my work on the Titan liquids for my American users to come over. And yeah, I think that's what I want to leave it at, to give chance for people to ask questions. I hope it's yeah, not too quick, and hopefully some of that made sense. But I'm always here to chat to, and as I said, I'll be over at EPSC with a booth, so we can chat in person as well if you want. But yeah, all right, I'll leave the floor then to questions.
Thank you so much, Zach. That was fascinating. And something I'd love to add, having visited ISIS and Diamond earlier this year, what I wasn't prepared for was two things really that really surprised me about some time spent in the visit. The first was the sheer scale of the facilities, that they're completely staggering in size, and the kind of scale of the operation, the amount of people that are involved, the amount of resource, the amount of strategy that goes into maintaining these things is excellent. And the second was the friendliness and the personality of the staff as well. So a real hearty recommendation to work with Zach and the guys at Isis and Diamond, because yeah, they're a good bunch with a super interesting facility. Okay, we have some time for questions now. Get your questions for Zach into the Q&A or in the chat, and Martin and I will read them out. Zach, I see you've also got your email address there on the screen. Is it okay for people to
Yes,
email you with questions
of
if they think of
course.
them later?
Yeah, of course. I'm always
Brilliant.
open, and if I don't always know the answer, I of course know which of my colleagues are the instrument scientists for different instruments. I can always pass you on. Um, Especially if you want to chat about any of the dynamics side of things, then I would definitely have to. I've seen so many talks, but they never quite. We all have our own expertise, right? But yeah, more than happy for people to email.
Super, thank you.
Let's see if there's one in the Q&A. So Tae Jung, he's working from MNHN in Paris. I don't exactly know what that stands for. I wonder if a sample single grain crystal or glass phase in 10 to 100 seconds micron in size.
Well, in terms of if that's enough for
Okay,
for
is it possible to apply any of those technique you mentioned to the sample? What are typical size limitations to have acceptable data quality?
So yeah, so it is a sort of mixture of the sort of size of your sample, and I mean sometimes you can also just measure for longer. I mean that's not unheard of. So if it can't be made bigger, I'm not entirely sure of how big or small crystallography tend to want theirs. I can always double check with it, but it's probably fine. And if it because our beam sizes, I'm not entirely sure for crystallography instruments. For our ones. It's probably more, we probably need slightly bigger, but it might be fine as long as you just measure it for much longer than maybe we would for others to get the same amount of statistics that you would need to get really good resolution. But it depends again on the instrument, because some instruments are made to deal with smaller samples and are made by having better detector coverage or a higher intensity of a beam and so on. So it's probably fine, or definitely something that can be worked around. I mean, especially if depends also if you would be happy enough for it to be powdered, because at least on the crystallography side, that doesn't tend to affect the sort of atom to atom length scales that you're looking at. But of course, it depends on the sample. But there's no reason why not. I mean, my view is always there's so many facilities and we have so many instruments, and a sample will find a way. There's always a way. So I'll say yes in some fashion.
I guess that Taejang will have to submit a proposal to find out.
Just
Um,
email, then I can find out.
and he is thanking you. Okay.
No bother.
All right. So there's no other questions at the moment. I was wondering, so what in terms of Europlanet has already, how many applications have there been from the Europlanet community? Oh, there's another question coming up, but
Well, I'll say so. This is fairly new. So we only became a member this January, I think it was. So far it's just been the one of the alkanes that we've done because the proposal for us was in April. So we have a proposal around April and in October. And so that's every year that we have those two. And now Europlanet usually only has the one call, which was earlier this year. But I think now that we're going to have another one in autumn as well to and carry on like that from now on to better encompass facilities like ISIS in the fact, of course, we have our own proposal deadlines that have to kind of link up well with Europlanet. So far it's been the one, but we're hoping to build now. And I'll also add actually that my colleagues at Diamond are also interested and they might potentially become Europlanet members as well next year. Don't want to promise, but that's what we said. But my colleague, one of my collaborators, will be joining me again for the booth from Diamond. So again, if anyone wants to also speak from an X-ray standpoint or using both, then plenty of time to chat about that.
Super exciting. Thanks, Zach. And yes, just to echo what you said, we've had one transnational access call already in 2026. We'll be having our second call in the autumn. We're hoping to launch at EPSC. So if you've been eyeing up the Europlanet TA program, transnational access program, now is a really good time to be thinking about our facilities. I'll put a link in the chat in just a moment. Our next question comes from Adrian, who asks, what about passive neutron detection from space? Is the underlying principle similar to that of the active detection you described?
Well, I guess, well, it's the same. It'll be the similar types of detectors at the end of the day. I mean, we do have an entire detector team at ISIS who are constant. I don't. It won't be the exact same type of detectors because things are getting more and more advanced for our ones. Because of course it's a much higher intensity of neutrons that we have to detect coming in, and we have very different remits in terms of course, we have to have detectors that are specifically made for specific angle coverage and so on. But I assume the mechanisms will probably be the same. But I'm not going to pretend to say that I'm an expert on people that are detecting neutrons from space. But it should be the same mechanism of detection that we use. But ours will be, of course, yeah, more focused on higher intensities and specific angle coverage because of the fact that that has to do, of course, with what we're looking at in our sample. And the same also with we have specialist detectors, of course, for the imaging and specialist detectors for the ones looking at dynamics, because there you're more focused on energy transitions. And it's and this is why, as Cam says, we have so many groups of engineers that are specially dedicated to different things. So a detector group, but we have then also pressure and furnace for anyone who wants to do. You have high vacuum, high pressure. There's specific engineers that focus on that. There's a whole cryogenics one as well for anyone wanting to do cold things. It's yeah, luckily it means that I don't have to understand everything, which is great. But yeah, hopefully that made some level of sense.
Okay, we have another question here from Gwen Young. I heard that water ice has at least 15 different structures from ice 1 to 15 and maybe more. I wonder if the neutron scattering also contribute to discover what kind of ices exist on the surface or under the subsurface of planetary bodies.
Yes, so we've had a lot of ice work, especially in crystallography, doing pure water ice. And one of my collaborators, Christoph Saltzman at UCL, has done a lot of this, of discovering, of looking at different phases of ice, whether it's under, I know crystallography have done a lot of high pressure studies of trying to look at, yeah, different phases of ice in planetary bodies. They have a special thing called a Paris-Edinburgh press, which is made to go to huge amounts of pressure. And they have used that to discover different phases as might be relevant to different planetary bodies. And yeah, so I mean, on my side, at least, stuff I've personally done has been more looking at the low pressure stuff and the more amorphous things from the vapor deposition. I have also been personally involved in some OU work, which is looking at salty water, so water ice that's mixed with salts, so specifically NaCl to do with icy moons and the processes there with Rachel and Mark over there. And that again was using these crystallography and diffraction instruments because you can use that, of course, to mark out different phases. And we found a new phase of this ice at certain temperatures. And so that all again comes to the beauty of neutrons, of using these complex sample environments, especially for planetary stuff, that we can do the high pressure stuff easily. We can do low temperature and high pressure together very easily, or the opposite of low pressure and so on. So yeah, there's been quite a few studies looking at different ice phases across different things. But of course, as you said, there's a million different phases and more things to find, and of course more mixtures to do, which is stuff I personally get involved in. But anyone that's doing anything like that you may know of, or you yourself watching, please don't hesitate to connect. Like, that's a very simple experiment for us to do because we have done plenty of it before.
Yeah. I know that there was ISIS in the solar system workshops or conferences
Mm.
in the past. I don't know if they continue to be there, but that's maybe later.
I don't think we've done as many, but I'm hope we will. So I guess I'll also mention we are going to host a conference at ISIS with Europlanet next year, which of course then we can bring more and more of these studies to light for people to find out more about and so on. But yeah, ISIS have it because we are in the same lab, Rutherford Appleton lab, as RAL Space. There has been in the past, yeah, lots of sort of more space related things, but there's not as much space related research in our ISIS user community as I would like, which is why I'm doing this, to try to reach out and say there's lots of potential. Please come and chat. It's kind of, yeah, where we're at.
Thank you. Our next question comes from Veli in the chat. Love to see Veli. For those of you who are familiar with Europlanet webinars, Veli was one of our speakers earlier in this year, I think. So welcome back. Veli says, brilliant talk, Dr. Amato. What is the imaging resolution, i.e., how small are the things that you can image?
For the neutron imaging side, I I don't think it's now. I could be talking absolute rubbish, but I don't think you can go, of course, as small as electron microscopy or something. I think this is more, at least from what I've seen, people tend to use this more for kind of larger things. So they've used it a lot, and that's probably to do with the detector coverage. So they've been more focused on bigger things. So I've seen them look at cavities in teeth. I've seen them, yeah, look at, of course, the roots in plants. They have also just looked at big things like engines and so on. And they've actually recently added in to our imaging instrument is called IMAT, and they've recently just put in two big diffraction detectors, so you can simultaneously image and also get a diffraction pattern of what you're looking at, which of course will add a lot more remit. But I'm not entirely sure just how small. At least I don't think I've in any talks seen anything quite as small of yeah, what you might get with electron microscopy. I think it tends to be for larger things, but there might be other instruments and other facilities that can go that small. I don't see that there's any reason why not to. But I have also seen there's a lot of people from archaeology that use this instrument because they want, like I've seen them do it where they've looked inside of, special vases because they of course can't break them open. So they use the neutron scattering to look through. So far as I've seen it, their user community tends to be more on that side. But as with anything, all groups are very keen to expand capabilities. They just sometimes need an application, and that's where it's always worth chatting to people.
All right. So the Antikythera mechanism may be passed in your hands at some point, right? No? I
Who
don't know.
knows?
Anyway, there's an anonymous question. In your amorphous ice experiments, poor coursing occurs before and during crystallization. Do you expect volatile release to be controlled primarily by the evolving pore network or by the amorphous to crystalline transition itself?
So that has been actually, so yeah, most of our previous work over about 10 years before I, started in this was doing pure water ice. And towards the end of my PhD, which is now we're more working on, is adding adsorbates into our ice to look at exactly that, to understand what's happening. We do imagine it, I mean, it would be a mixture, right, of, yeah, of course, we see that there's some level of pore collapse, even pre the glass transition of 120, even lower on, and all of these things. There's been lots of different experiments looking at that. So I think it is always a mixture. But what we wanted to see, because we can see that there's still some porosity left over from void volume after the fact, of crystallization, that there is maybe potentially likelihood of things still being able to be stored in until it actually desorbs off of the surface. But that's what we're looking at. So we've done some experiments with that same setup of having our ASW with CO2 mixed into it. We're going to do now some pure CO2 ice because we need that to kind of discern what's happening in this mixture. And we're going to continue with other adsorbates and see and look into that and try to get a better grip on it because it is, of course, such a interesting and important thing to understand what's happening there, especially from the planet formation side of chemistry going on. So that's, yeah, we're exactly on that trajectory. So hopefully at some point I can give you some more answers, but keep a lookout for this always takes a bit of time because with our one, we try to make our ice very low flow rates so that we can make sure that it's amorphous. So it takes in 8 days of beam time, we maybe do about 2 or 3 samples because it's 12 hours of deposition, which is at a very low flow rate. We're making a very tiny amount of material. Luckily, on the instrument we use, there's enough resolution that even with a small amount of ice, we can still see it. And then we anneal at very specific steps and very specific heating rates, which can mean that we sometimes anneal for 20 hours or more. So as you can see it, then it's, so it does take quite a lot of beam times. And so that takes a while to get all this data and get all this information out. But hopefully soon enough, we can get some more answers on that.
Thank you. Our penultimate question for now comes from Mads in the Q&A. Mads says, "Hi, Zach. Great talk. I was curious about what the ongoing high-pressure sample environment developments are and how those might be applied to planetary science. In particular, what are the challenges with doing neutron PDF at high pressure?" From University of Cambridge in the UK.
So I think as far as because I do, one of my collaborators is exactly an expert on doing PDF of high pressure material. She hasn't though done it in terms of planetary science. So I could, if you want more, I could get a proper answer from her. But I think some of the issues, I think at least I always hear as on the PDF side is just can be sometimes amount of sample. But as far as I've seen, they have been able to do plenty of PDF work on high pressure materials. But she's done that with, you can do that with X-rays as well. They have these things called diamond anvil presses that they use for it. I recently saw that they're getting the issue with the diamond anvil press is because of the problem with X-rays is it's less easy to have these sort of things. So they've been trying to figure out if it's easiest to have it where that the X-rays go through the diamonds or through it there. But then there's a difficulty of, amount of sample and how making sure that you're hitting just your sample and so on. From a neutrons perspective, I know the crystallography. I have used their Paris Edinburgh press a lot to look at different materials and that. And I'm not entirely sure if they've done PDF analysis or if they tend to mostly do what they call Rietveld refinement, which is modeling, fitting your Bragg peaks and so on to then get out an entire crystal structure and so on, which does, of course, if you have a crystalline material, does a fantastic job at giving you all the information you need. But yeah, of course, and I know that they have also looked at defects in crystals. So I assume that it is perfectly feasible. But yeah, I don't think there are necessarily many problems. I think these are things that they're actively doing. It might just not be relevant to planetary science yet. At least of the planetary science ice work I've seen from the group, it's been mostly doing that Rietveld refinement to get crystal structures out, which seems to be their bread and butter. Of course, that's what they're great at. We in our group, of course, our instruments are very much dedicated to PDF studies, and not just PDF studies necessarily, but that's our thing. But we don't do as much high pressure things, but I don't think there's any reason why we couldn't put a Paris Edinburgh press into ours if the resolution was better for PDF there. It's kind of a lot of our sample environments can be kind of flexibly used on different instruments. We're quite good at doing that. So if there are problems on one, we can always bring it to another. So I mean, most of the time with neutrons, it's just an issue of have you got enough sample? It's kind of there, but we're always on hand to help with things like that. And we have especially also if you have to do a deuterated version of your sample. We have an entire deuteration lab and team that can do it for you, depending on what it is, or they can help you and give you advice on synthesis steps and things like that as well. So that can also be hopefully of some help. But yeah, but obviously feel free to message, and I can always, if you want to properly chat, I can put you in contact with the crystallography group who will be best to give you the full ins and outs of it all.
Okay, I think that probably takes us to the end of our Q&A then, and rather tidily to exactly on the hour. So well
Amazing.
done. Well done, everybody. Well done, team. Okay. Thank you, everybody, for joining us for this Europlanet webinar. Thank you so much to Zach for an
Yes,
excellent
absolutely.
talk and most agile response to the Q&A. So thank you. As a reminder, you can catch Zach again at EPSC with other colleagues at our exhibition. So please bring your questions, bring your curiosity to that. Okay. This recording will be put up online very shortly. Thank you, everybody, for joining. Lots of positivity in the chat, which is fantastic. Okay. I will hopefully see most of you at EPSC in The Hague in just a few weeks' time. I'm looking forward to it.
Absolutely.
We'll see you then.
Okay. Goodbye, everyone.
Bye,
Thank you so
everyone.
much.
Thank you guys. Thank you for coming.